Hello and welcome to another in my series of videos about derivatives and how to find them. And this video is about what's called the product rule, which is a rule you can use when the thing you want to find the derivative of is a product. That is, it consists of two things multiplied together. Now at this point, if you've been watching my previous videos or if you've been studying these derivative rules in the order that they are traditionally presented in a calculus class, you've already learned some basic derivative rules. Like, for example, that the derivative of a constant times a function is the constant times the derivative of the function. And the derivative of x to a power is the power times x to the power minus 1. And the derivative of a constant by itself is 0. And the derivative of two things added together is the sum of their derivatives. The derivative of two things subtracted is the difference of their derivatives. So it might be natural to think that the derivative of two things multiplied together should be the product of their derivatives. But does that really work? Think about the function x squared. Now we already know what the derivative of x squared should be. Since it's x to a power, the derivative should be the power times x to the power minus 1, which in this case would give us 2x. But if we think of x squared as x times x, because after all that's what x squared means, and if we try to take the derivative of the first x times the derivative of the second x, we get 1 times 1, which is 1, which is clearly not the same thing as 2x. Or another way we could think of x squared is as 1 times x squared. So if it really worked to take the derivative of the first thing times the derivative of the second thing, we ought to be able to take the derivative of 1, which is 0, times the derivative of x squared, which is 2x. But 0 times 2x would just be 0. And that's obviously not the same thing as 2x. In fact, if this were really the rule, then we could take any function and write it as 1 times itself, and then take the derivative to be the derivative of 1 is 0 times, well, we just always get 0. So obviously that can't happen. So this is not the correct rule for finding the derivative of a product. Okay, so what is the correct rule? Do you want me to just tell you? Or do we want to see if we can figure this out? Let's think about this and think what should happen if you have two things that are being multiplied together. Suppose we have two things that are changing. How does their product change? Like if you have x times y, and x is increasing and y is also increasing, what does that do to their product, x times y? Because after all, the derivative is supposed to measure the rate of change of something, how fast it's changing. And we can call the individual things that are being multiplied together x and y, although that might get a little confusing because we usually think of y as a function of x and x as just the variable. We could call them f of x and g of x, and that's what I am going to call them later on. But for now, I don't want to think about how they depend on x. I just want to think of two things that are both changing. So I'm going to call them u and v. So you got u that's changing, maybe increasing a little bit. You got v that's also changing, increasing a little bit. What happens to u times v? How does that change? Well, if we add on a little bit more to u, call it du, and we add on a little bit more to v, call it dv. So the new product now is u plus du times v plus dv. And you can picture this geometrically. You can think of u times v as the area of a rectangle that has a length of u and a width of v. And if both of those dimensions change, if they both grow by a little bit, u increases by some small amount du, v increases by some small amount dv, the whole rectangle is going to change by how much? Well, you can see it algebraically, and you can also see it geometrically. The new rectangle, after u and v have both expanded a little bit, the size of that new rectangle is going to be u times v plus u times dv plus v times du plus du times dv. You can think of multiplying out the two binomials u plus du times v plus dv. So you could use the FOIL method on that and get uv plus u times dv plus v times du plus du times dv. Or you can visualize that geometrically by thinking, okay, if u expands horizontally by a small amount du and v expands vertically by a small amount dv, then we've added on this thin strip at the top that's u units wide, or u units long and dv tall. We've added on this thin strip over here that's v units tall and just du wide. And we've got this little tiny square up here at the top. So in place of the old value or the old product or the old area, uv, we have a new area or new product, uv, which is the same as the old area, plus the amount that it has changed by. And that amount that it's changed by is u dv plus v du plus du dv. That is the original value of u times the amount that v has changed by, plus the original value of v times the amount that u has changed by, plus the two changes multiplied together. And if they were both very small changes, then multiplying those two very small changes together gets you a really, really tiny change. So if du and dv are both very small, then this little square or rectangle or whatever it is up here is going to be really, really tiny. And in fact, in the early days of calculus, they would have said, okay, now think of du and dv as these infinitesimally small changes. And then when you multiply them together, du times dv is so small that you can just forget about it. You can just ignore it and pretend it's not there. Now, that's probably not completely rigorous. So in a little while, we'll come back and give a more rigorous proof of what happens. But this kind of suggests that the amount that the product changed by was the first thing times the change in the second thing, plus the second thing times the change in the first thing, plus that third bit that we said was so small that we could pretty much ignore it. So based on that, the product rule says that the derivative with respect to x of a product, f of x times g of x, is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. It's f times g prime plus g times f prime. Or if you want to use the u and the v symbols, we could say the derivative of u times v equals u times the derivative of v plus v times the derivative of u. In words, this would just be you take the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So notice that each one of these two factors gets multiplied by the derivative of the other factor, and then those get added together. So that is the product rule. So does this work on x squared? Like if we think of the function x squared as x times x multiplied together. Well, the product rule would say to take the first thing times the derivative of the second thing, so x times the derivative of x, plus the second thing times the derivative of the first thing. So this x here times the derivative of this x here. So everywhere we took an x, that's the x. Everywhere we took a derivative of an x, that's a 1. So we got x times 1 plus x times 1. That would just be x plus x, which is 2x. So using the product rule does give us that the derivative of x squared turns out to be 2x. Or what if we thought of x squared as 1 times x squared? What if the two things being multiplied together were a 1 and an x squared? If we use the product rule on that, think of that as f times g, where the part of f is being played by 1 and the part of g is being played by x squared. Then for the derivative, we get 1 times the derivative of x squared plus x squared times the derivative of 1. Of course, the derivative of x squared is 2x, and the derivative of 1 is 0. Remember, the derivative of just a constant by itself is 0. So we got 1 times 2x, or just 2x, plus x squared times 0, which is 0. And then, of course, 2x plus 0 is 2x. And notice what happened here. We did have a constant times a function. And we already have a rule for that kind of a situation. We have a rule that says the derivative of a constant times a function is the constant times the derivative of the function. Now, we don't really need that rule if we have the product rule, because the product rule would tell us to take the constant times the derivative of the function plus the function times the derivative of the constant. But then that part of it, where we have the derivative of the constant, that part is just 0. So we do end up just getting the constant times the derivative of the function. So in a way, this constant multiple rule is kind of a special case of the product rule. Now, what about the proof? How do we go about proving the product rule, that the derivative of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x? Now, if we go back to the definition, how derivatives are defined in terms of the limit of this difference quotient, the derivative of f of x g of x would be that function, but with the x's replaced by x plus delta x, minus that function just with the x's in place, all over delta x, and then we take the limit as delta x approaches 0. So that's what the definition says that the derivative of f of x times g of x should be. And we need to show that that's equal to f of x times what the definition says the derivative of g of x should be, plus g of x times what the definition says the derivative of f of x should be. So how do we get from this to this? It's not immediately clear or obvious how to do this. This is not as simple and straightforward as some of the other derivative rules were. And if you look at the proof of this in a calculus textbook, the first line of the proof, the first thing you do to get from this to this, is kind of a trick. It's something that you probably would never think of doing yourself. Now, once you see somebody else do it, and you work through the rest of the proof, it turns out to work, and eventually you see, oh, so that's, now I see why they did that, is because it works out to give you what you need. But it's the kind of thing that you might never think of doing yourself. So let's think about this for a minute, and I'll try to motivate that trick so that it doesn't just come out of nowhere. Let's focus on our goal, what we're trying to get to here. And one thing I could do is take the f of x here and multiply it through, and take the g of x here and multiply it through by this. After all, a constant times the limit of a function is the limit of the constant times the function. And something like f of x or g of x is treated as a constant as far as these limits are concerned. X isn't going anywhere, it's delta x that's approaching 0. And so if I go ahead and multiply through by f of x here, and multiply through by g of x here, and then these two fractions have the same denominator, so I can go ahead and combine them and put it all into one big limit, because the limit of the sum of the limits equals the limit of the sums. So now it's all one big limit as delta x approaches 0 of f of x times g of x plus delta x minus f of x times g of x plus, and then over here we have f of x plus delta x times g of x minus we have f of x times g of x. Okay, so we need to get from this to this. show how these two things are equal. Now, this one ends in minus f of x g of x. And so does this. So that part, at least, is already the same. Now look at how these begin. This one begins with f of x times g of x plus delta x. And this one begins with f of x plus delta x times g of x plus delta x. So they're sort of almost the same, except that this one has an f of x, where this one has an f of x plus delta x. And that's all there is to this, but this has a couple other terms in the middle. It has a minus f of x g of x, and it has a plus f of x plus delta x g of x. And this f of x here, well, both of these f of x's, they're not quite the same as f of x plus delta x, but if they were, if this was really f of x plus delta x in front of this g of x here, then these two middle terms would just cancel out. One of them's minus, one of them's plus, and if this really was an f of x plus delta x, then minus f of x plus delta x g of x plus f of x plus delta x g of x, that would just add up to 0 and get out of our way. So it looks like the thing we need to worry about is the difference between the f of x's that we have here and the f of x plus delta x's that we have here. So what is the relationship between f of x plus delta x and f of x? And really what we're interested in is the relationship between their limits. Those are things we're taking limits of. So what's the relationship between the limit as delta x approaches 0 of f of x plus delta x and the limit of f of x? Well, that second limit would just be f of x. Because as delta x approaches 0, f of just plain old x doesn't depend on delta x. It's constant as far as delta x is concerned. And what about this one? Well, the x plus delta x would be approaching x plus 0, or just x. So the thing that we're taking f of is approaching x. So now the question is, does f of that thing approach f of x, if that thing is approaching x? Does that mean that the limit as delta x approaches 0 of f of x plus delta x, that's equal to f of what the x plus delta x is approaching, which is x? Well, it does mean that if f is a continuous function. That's what it means to be continuous. It means that as the independent variable approaches some number, f of that independent variable is approaching f of whatever the limit of that independent variable is. So, is that true here? It's true if f is continuous at x, and we are assuming that the derivative f prime of x does exist. That is, f is a function that is differentiable at x. But there is a theorem that says that if a function is differentiable, it must be continuous. I had a video where I introduced the subject of derivatives, and I talked about what differentiability means and how a function might or might not be differentiable. And if it's not continuous, then it can't be differentiable. But if it is differentiable, it must be continuous. So we are allowed to safely conclude, assuming we have a function here that can be differentiated, that this limit here, the limit as delta x approaches 0 of f of x plus delta x, is f of x. So with that in mind, I'm going to stick in sort of what we've got here, but with an f of x plus delta x here. So I'm going to take what we start with and stick in the middle here something that is equivalent to 0. So I've really just added 0 to the numerator, but that 0 is in the form minus something and then plus that very same thing. So the part in orange here adds up to 0. So I haven't really changed anything. I've just changed the way it looks. I've put in a minus f of x plus delta x times g of x, and then plus, I've added that very same thing right back again. Now we've got 4 terms altogether on top. And I'm going to group them so that the first 2 are together and the last 2 are together. On the first 2, I can factor out what they have in common, which is f of x plus delta x. So that's f of x plus delta x times g of x plus delta x minus g of x over delta x. And then the last 2 terms, I'm going to factor out what they have in common, which is g of x. So plus g of x times f of x plus delta x minus f of x over delta x. And now, if we take the limit as delta x approaches 0, this f of x plus delta x right here should have a limit of f of x. This part here, the limit as delta x approaches 0 of g of x plus delta x minus g of x over delta x is, by definition, the derivative of g of x. It's g prime of x. Then here we've got g of x. It's already constant as far as delta x is concerned, so the limit there is just g of x. And then the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x is f prime of x, again, by definition. So that completes the proof. We've shown that if you take what the definition says should be the derivative of f of x times g of x, you can show that that's equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. Okay, let's finish with a couple more examples of the product rule in action. Suppose we want the derivative of x times the sine of x. So this function is a product. It is made up of 2 things multiplied together. And neither one of those things is a constant. One of them is x, and the other is the sine of x. So we ought to be able to use the product rule on that, which tells us that the derivative of the whole thing should be the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. We just have to fill in what all of those things are. So the first factor is x. The derivative of sine x is cosine x. Plus then the second factor itself is sine x times the derivative of the x here would be 1. So we get x times cosine x plus sine x just times 1. And that's our answer. That is the derivative. F prime of x is x cosine x plus sine x. Okay, what about this one? Suppose f of x is the function 5x minus 3 times x plus 2. What's the derivative of that? Well, there's 2 ways we could approach this. One way, where we don't need the product rule, would be to just multiply this out, like with the FOIL method, and then find the derivative. So if we multiply this out, we have 5x times x is 5x squared. Outside we have 10x. Inside we have minus 3x, so together that's plus 7x. And then last, the minus 3 times the plus 2 is minus 6. So multiplied out, our function is 5x squared plus 7x minus 6. Now notice this is still f of x. I haven't differentiated anything yet. I've just written our original function f of x in a different way. A way that's easier to differentiate. So now here is the derivative. If that's f of x, then f prime of x should be 10x plus 7. It should be 5 times 2 times x to the first power plus 7 times 1 minus 0. 10x plus 7. But the other way we could do this would be, instead of multiplying it out first, just leave it as a product and use the product rule. So the product rule would tell us to take the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So that would be 5x minus 3 times the derivative of x plus 2 would just be 1. Derivative of x is 1 and the derivative of the constant 2 is 0. plus the second half of the product rule is to take the second factor, x plus 2, times the derivative of the first factor, 5x minus 3. And if we just wanted the derivative and we didn't care what form it was in or how simplified it was, we could just leave it like that and say, okay, there it is, there's the derivative. But let's clean it up a little. Let's multiply out. If you take 5x minus 3 times 1, that is 5x minus 3. If you take x plus 2 and multiply it through by 5, you get 5x plus 10. And then if you combine the similar terms, that simplifies to 10x plus 7. The 5x and the 5x add up to 10x. The minus 3 plus 10 is plus 7. So it matches what we got the other way. It's 10x plus 7. Okay, so that's pretty easy and straightforward once you learn about it and once you get the hang of it. The rule that's usually shown next is a little bit more complicated. It's not too bad, but it gets a little more complicated to remember and a little messier to use. It's what's called the quotient rule, and that is what you would use if the function that you want to find the derivative of is a quotient. That is, if it consists of something over something else. So that will have its own video all about the quotient rule.